So we have f of x, which is tangent x raised to 1 over x. Remember, we cannot use the power rule on this. It's not possible. This is a function raised to another function. So we can use the power rule, bring 1 over x down, and blah, blah, blah. Also, what I would like us to remember moving forward is that 1 over x prime is negative 1 over x squared. This will help us in the future, especially in chapter 5. So please remember, when we differentiate 1 over x, we get negative 1 over x squared. You can say, how come? Okay, let's do this one time by, step by step. I replace 1 over x by x to negative 1, and when I differentiate, I bring negative 1 in front. I subtract 1 from the power, and then I should multiply by x prime, but that's 1, right? So there is no need. So this is negative 1 over x squared, and that's how we get it. So moving forward, please try to remember this. And you can always prove it. You don't have to memorize it. But it's good if you can, because it will save us a lot of time. Okay, so now we're back here. The only chance we have to differentiate that function is to apply natural log to both sides. So natural log to the left-hand side, I'm going to replace f of x by y. And natural log applied to the right-hand side, I keep natural log on the left, and then I bring 1 over x in front. So now I have a product of function 1 and function 2. This is function 2, and this is function 1. The next step is what? Can anyone tell us what to do next? Differentiate, exactly. Very good. Differentiate. The left-hand side, implicitly, 1 over y times dy over dx equals the first function prime, which we already know now, negative 1 over x squared, times the second one, plus 1 over x. I copied the first, but now I have to differentiate natural log of tangent x. It's 1 over tangent x times the inner function prime, which is secant squared. Better? Perfect. I simplified it a little bit. I'm fine if you don't. But you have to write dy over dx. You have to multiply both sides by y. And we prefer the original y, which is tangent x raised to 1 over x. Then this is negative natural log tangent x over x squared plus secant squared over x tangent x. So I'm fine with that. You'll see in the solutions I went one step further, and I changed the tangent, 1 over tangent into cosine over sine. I simplify. Well, it's not important, really. You don't have to do that. I just wanted to simplify it a little bit. See if it takes us anywhere, but it didn't, so. Very good. Other questions for me before we continue? Other questions? Okay, I would like to look at problem 4 on this handout. I would like to look at problem 5 on this handout. And I would like us to look at the extra credit on this handout. This is not for a grade or anything, but I'd like you to start with problem 4. So let's work on problem 4. A couple of minutes, think about it, come up with an exam, with an equation, etc., etc., etc. So two boats leave a port at the same time. One travels west and the other one travels south. At what rate is the distance between them changing 30 minutes after they leave the port? Now, I would like you to notice the measurement unit. We can't have hours and minutes in the same problem, right? In the same equation. So I recommend change the 30 minutes into half an hour and leave the miles per hour alone. So let's work on this. I wasn't happy with this past quiz, so I think, of course, I do not keep all quiz grades, so no one will fail the class because of a quiz grade or 2 quiz grades. But I really want us to work a little bit harder. And maybe I should just give a little bit more work in class. So. I'm worried. You know my middle name, right? What is my middle name? Worry. Worry is my middle name. I didn't get a chance to run to the bathroom. I'll be right back. Okay, let's get it started. And then we have 2 more to look at. Ready for this? Okay, so first, remember to read the problem at least twice. Okay, you get one? Okay, perfect. Okay, so please read it at least twice. It says they leave from the same port at the same time. One travels west and the other one travels south. And this one travels at 20 miles per hour. And this one at 15. And whatever we are asked to determine is when t equals 0.5 of an hour. We've done this problem before with different numbers, correct? Okay, perfect. So what would you say? What are we asked to determine? No. dw over dt. This is the question. When blah blah blah, and remember this has to wait. Okay. So now after we establish what we are given, and we have what? What does 20 miles an hour mean? Perfect. Over dt. What does 15 miles an hour represent? Very good. dy over dt. Perfect. Now what? I need a relationship, an equation that has all these in it. So I can find dw over dt. Very good. W squared equals, awesome, plus, great. Now remember, all these three are of t. Very good. Thank you very much. Functions of t. Functions of time. Good. Can anyone dictate the next step? Anyone dictate the next step? Thank you. Good. We are ready to differentiate, please. Two W. Perfect. And the same thing, 2x dx over dt plus 2y dy over dt. And of course, we're going to divide both sides by 2. All terms have 2. You can drop it. Perfect. Next. Remember, these are given. We're asked to determine this. So we will divide both sides by w. That's it. That's all we have to do. And then t equals 0.5. So this will be x dx over dt plus y dy over dt. We do not have w, but we can solve this equation for w. So from here we have the square root of x squared plus y squared. So now we have to find all these numbers. We only have dx over dt, which is 20, and dy over dt, which is 15. And now we have to determine x, y, and then the w will be there. Can anyone give us x? So it's 20 multiplied by 0.5. Very good. Do we all agree with 10? Everyone? So then this piece is 10. Can anyone give us y? Yes, very good. Or 7.5. So then this one is 10 squared and this one is 7.5 squared. I'm going to write it one more time with the numbers in it. So dw over dt when t equals 0.5 of an hour is 10 times 20 plus 7.5 times 15 divided by the square root of 100, oops, plus 7.5 squared. Do not put the power on the 100. I already squared it. So let's put this in the graphing calculator. Do we all understand the steps? Any questions on this, please? Okay, so let's put in the graphing calculator. In y equals, no, of course not. I got carried away. I was looking at that function. So parentheses are on the top. 10 times 20, I can write 200 for that, plus 7.5 times 15. everything parentheses, close parentheses, and divided by the square root of, in parentheses please, 100 plus 7.5. If you have a sophisticated calculator, you may not need to put parentheses, but I don't trust the system here. Okay, that's it. So 25, measurement unit. If you just write 25, I will not be able to give full credit.
Did you put 10 for her?
It was 20 times 10, and I put directly 200. I'd rather go back and check. Let me see. Everything is okay? Do we get 25? Okay. Measurement unit. Miles per hour. Yes. It's the rate of change of distance with respect to time. Great job. Moving on. This is a problem that we have not gotten to look at. Now it's the time. And this one, at what rate is soda being sucked out of a cylindrical glass that is 6 inches tall and has a radius of 2 inches, knowing that the depth of the soda decreases at a constant rate of blah, 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 inches per second. So which one would you like to continue with? This should be okay. This, I have not shown it yet, so I have to explain all the steps on this one. So let's work on the last one and then we come back. So a can of soda is a cylindrical solid, right? Imagine this. This is not a soda, but this is the cylinder, right? A right circular cylinder. Good. So we are asked to connect the rate of change of the height with respect to time and the rate of change of volume with respect to time. Anyone remembers, we talked about that last time, anyone remembers the volume of a cylinder? Times? Very good, awesome. So that's our starting point. The volume of a cylinder, pi r squared h, where this is the height and this is the radius. So the cylindrical glass or can, whatever that is, it doesn't really matter. So the height is 6 and has a radius of 2 inches. Knowing that the depth of the soda decreases at a constant rate of this. So the h over dt is given to us, 0.25 inches per second. And we want to find the rate of change of volume with respect to time when they're not telling us when, so they only want us to determine the rate of change, which is fine. We don't have to plug in anything. So what do we have to write? dB over dt equals. So 2 squared is 4 pi, right? Because we're given that is fixed. We cannot change. Okay, so this is times dh over dt. We don't even have anything. We can replace this by 0.25. That's all. So 4 pi divided by 4 because 0.25. So this is pi. Measurement unit. Measurement unit. Very good, awesome. Cubic inches per second. Perfect. So now allow me to explain number 5. Any questions on this? Too easy to mention, right? Good. Okay. So let's talk about the cost function. I'm going to copy it. So the cost function c of x equals negative 0.2301 x cubed plus 0.005 x squared plus 60x plus 800. So this is our cost function. First question, find the marginal cost. It's a derivative, but we call it a marginal cost. That's the name of the derivative of a cost function. The same thing with marginal profit or the marginal revenue, etc., etc. So then c prime of x is negative 0.0003 x squared plus 0.01 x plus 60. Do you agree with this function as being the derivative of the cost function, also called marginal cost? Agreed? Okay, part B is asking us to find c prime of 100 and interpret its meaning. Okay, so let's plug it in. I need to use the calculator as well. I got 58. Please correct me if I'm wrong. 58 without a measurement unit means nothing. It's a rate of change, so it has to have two measurement units, one coming from the top and one coming from the denominator. It must be the rate of change of something with respect to something. So let's read the problem one more time. The cost in dollars of producing X units is. So c prime of 100, and we have to explain its meaning, but we also have to find its measurement unit first.
Dollars per unit?
Of course, thank you very much. $58 per unit. Now we have to explain its meaning, and we can put it in writing. This is the rate of change of cost with respect to number of units exactly when we manufacture how many units?
100.
Exactly. One more time. So this is the rate of change of cost with respect to number of units, or per unit, better, when we manufacture 100 units. Now the question is what it predicts. So let's put this in writing. So 58. So I think this is 3, 4. So c prime of 100, rate of change of cost per unit when 100 units are produced. Now this is the next sentence is very important. C prime of 100 predicts the cost. It's not the exact cost, but it predicts the cost of which item? The next one. It predicts the cost of the next item. It's not exactly the cost of the next item, but it predicts the cost of the next item. Compare your answer from part B, which is that 58, with the cost of producing the 101st item. So this is an approximation. Approx. The exact cost of the 101st item is determined how? Cost of 101 minus cost of exactly. This has nothing to do with the derivative. So the exact cost that the additional cost that we have to pay, or the exact cost we pay to produce number or unit 101, is the difference between producing 101 and producing 100. When we subtract these two, the answer would be the exact cost of producing one more item. So now I will put in y equals, I will put this function, which is negative 0.0001 x cubed, and then plus 0.005 x squared plus 0.01 x plus 60. Did anyone else get to 58 for the average, for the marginal at 100? Yes? Okay, perfect, thank you. So now second and table. All I want to plug in, oh, I'm sorry. All I want to plug in is 101 and 100. I messed up the function probably. What did I do?
You put 0.1 to 0.3. When? Are you putting the first?
The function, yes, the function itself.
Oh, the function. You put
What did I do this time?
16.
Oh, I forgot. Yeah, I forgot. Yes. Okay.
You put 1.
3, 2, 1, 60. Okay.
And then 0.01.
I know exactly I messed up because the answer has to be close to 58. It must be. I mean, it's math. You can't go around it. So I copied part of C and part of C prime. Well, I'm very good at that. Okay, plus 60x. Sorry about that. I wasn't trying to see whether you were paying attention or not. No, not at all. I wasn't paying attention. Good. So now second in table. Please give me the right answer. Thank you. So for producing 101, 6808, if you want, you can, there is no, no need for the decimal points, but because, I mean, I want to copy those, at least two. So 6807.9749 minus, okay, scroll down, 6750. So we can see indeed how close this is. So when we subtract these two, what do we get? So 9744, and we get 7, and we get, is it 5? How close are we? 57.97 versus 58. Very close. Which one would you prefer? To find the derivative and plug in one number, or you want the exact, so this is exact. Now, if we're talking about human life, no, I don't want 58. I want 57.9744. If we talk about medication, we can play with that. I don't want 58. I want 57.9744. But if it comes to the how much it costs to manufacture the next pencil or the next yard of carpet, I don't care for 58. And I don't care for 57.9744. I care for 58. So I know roughly what it is. So it depends. But this is a very good approximation of this. But again, we have to cross the, decide what's important. But this is the way we do it. Very good. Questions? Any questions? Do you think we are okay with related rates? And the answer should never be yes, because there are tons of different situations, tons of problems, on and on and on and on. Do you think we should work more? And we can always come back and we can review again for the next test. Or we will definitely do that. We will use an entire session to review for the test. So do you think for now we are okay with related rates? Would you like to work more on related rates? Okay, in that case, let's continue with linear approximations and differentials. So this is section 3.10, linear approximations and differentials. What's all this? What's all this information here? Linear approximations, what is that? And differentials, what is that? I'm going to start with differentials. And then we'll talk about the linear approximations. Okay, so let's go back to our favorite drawing. This is our favorite drawing. And you'll tell me how many times we saw this. How many? We don't even remember. Good. Of course, I have a point, and that's point P. Okay. The x-coordinate is x. The y-coordinate is y. Or f of x, of course. Then I'm going to draw a tangent line to the graph of f of x at P. Tangent at P. And I'm going to say that there is an error. It will look huge, but it's a minor error, but I need huge to explain. So let's say we have x plus dx, or x plus delta x. What is this? What is this piece? If this is x and this is x plus delta x or dx, what can this be? How wide is it? No, this is x and this is x plus dx, so this is just dx, which is delta x. And this is, we've seen this before, this time we're going to call it an error. Or minor change in x. I'm going to extend this vertical line. I'm going to draw a horizontal line through P. And now I hope you agree that I have created a right triangle. Now, can anyone give us the y-coordinate of this point? If you want to call it Q, let's call it Q. But I would like us to determine the y-coordinate of this point. We had h before. Now we have dx. Same thing. But I need dx now. So what is the y coordinate of Q? F of, very good, x plus dx, or f of x plus delta x. Nothing new so far, just a slight different notation, right? I would like you to tell me what this represents. So let's go back for a second and analyze this with an example. So let's suppose I manufacture discs. And when I manufacture discs, I realize that I have a minor error in the radius of the disc. So instead of having 3 inches, I have 3 inches plus a little bit. So if I made an error in the radius of the disc, that would trigger an error in the area of the disc. Let's say this function is the area of the disc. So I made an error in the radius that translated immediately in an area of the an error in the area of the disc. So then, what is this difference? We're talking about the y values. We're talking about the function. So for a minor error in the radius of the disk, I created a corresponding what? Change or error in what? In the y, or in the function value, in the area. So then what will this represent? Exact change. Exact change in y. It's denoted by delta y. Can anyone express the delta y, the exact change or the exact error triggered by dx or delta x? Exact error or change triggered by dx or delta x. They are both the same. Can anyone give us the formula for delta y? When we talk about delta y, we're going to talk about delta x, although they are the same. What will you say? It's obviously this piece minus this piece, correct? So what is this piece? F of x plus delta x minus this piece. Very good. Do we understand this? This happened because there was an error in x. Very good. Now, my next step is, I would like to determine this. Obviously, this point is on the function. This is the exact difference created by delta x. This is not the exact difference. It's an approximation of this because I'm using the tangent. I'm not using the graph of the function. I'm using the tangent, so this will be an approximation of this. In this case, the way I graphed it, it will be an overestimate of this because obviously the green piece is bigger than the pink one. But the question is, what does this represent and how do I determine it? So I'm going to take this triangle out here so we can talk about it. This is the piece I don't know. Can anyone tell us this piece? What is this piece? Dx, that's good enough. Okay, this is the tangent at P. Can anyone give us the slope? Slope, oops, of the tangent at P. Can anyone give us the slope of this line? Forget about the fact that I have a right triangle here. Look at this function. Look at the way I drew the tangent, P, and everything else, and please tell me what is the slope of the green line. We've done this every day. Exactly. Excellent. So the slope of this line, slope, is f prime of x. Because the x-coordinate of P is x. Is there another way now? Now we come back to the triangle. Is there another way of determining the slope of this line? Yes. S rise, which I have no clue what it is, over.
Yes.
Very good. Rise over run, right? It's a line. I have the rise. You can say you don't. I agree. I have the rise and I have the run. So the slope of this line can be determined also by blah blah over the x. And they have to be the same. This slope, m, and this slope, m, must be the same. So from this relationship, I will wait for you to tell me what this is. And there is only one answer.
M times 2x.
Say it again.
M times 2x.
No, of course. And that is called the differential of y. We've been using this notation, but I did not tell you the names of these two pieces. Now it's time for you to hear what they are. This piece is called the differential of x. This piece is called the differential of y. What does it mean? It's the approximate change in f of x triggered by a change in x of dx. So coming back to the problem we looked at a few minutes ago. Well, actually, I didn't write anything here, so why am I looking there? There's no point. What is this? dy. This is the approximate change in the function for a minor change in x. This is dy. Okay? What is this? If it's the exact change, how did we call it? Delta y. So this is the delta y, and this is the delta and dy. dy is this, and this is the exact delta y. What is the error, so to speak? 1, because we want to create one more. We don't want to create 100, we want 101. So that's the exact change that is triggered by 1 unit change in x. That is the change in cost. So that's the delta y, and this is the dy. Okay, coming back. Where am I? Now, from this equation, dy over dx equals f prime of x, I want you to solve for dy. Because we have a formula for delta y, which is f of x plus delta x minus f of x, we have a formula for dy. So can anyone give us the formula for the differential of y? Say it again.
Yeah,
Excellent. It's just that we write it f prime of x dx. Indeed. Does it matter? No, it doesn't. But we will see later in chapter 5 why we have to keep it in this order. So let's go back and summarize this before we look at examples. And I still have something to say about it. So this was point P. We wanted to create one more unit or produce one more unit. And we wanted to determine the exact cost. So this is delta y. We wanted to determine, like in the previous problem, we wanted to create from 100 to 101. So dx is 1. Delta x is also 1, of course. We wanted to determine the difference, the actual difference in cost. And we got it. It was 57 point blah, 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 blah. But now we wanted to use the derivative and determine this. And this was our 58 in the cost function. That is the dy. This piece is dy. This piece is delta y. But obviously, we are talking about minor changes. So dy is approximately delta y is approximately dy. And this is a very important relationship. And we illustrated it basically with an example, right? So we got that dy was 58, and we got that delta y was 57.9744. So obviously these two are quite close to each other. Can anyone refresh our memory? What is the formula for delta y? And again, what is the formula for dy? I need to put them together now. The formula for delta y, f of x plus, because we are using dy here, I'm going to write this time dx, minus f of x is approximately dy, but I have to replace it. What does dy equal to? F prime of x dx. And in this relationship, I will move f of x to the other side. And let's interpret this. This is the most important relationship, in my opinion, in this chapter. Okay, let's discuss what it means, and then we'll look at we'll apply it in different situations. This really says that a function of 100 units plus 1 is approximately the function of 100 units. I'm giving you the example from before because it's still fresh in our memory. So the function of 100 plus 1, which was c of 101, can be determined approximately, not exact. This is not the equal symbol. It's approximately f of 100 plus the derivative of 100 times this unit, which was 1 in our case. So f of x plus a little error is f of x plus an error in y. Okay, so let's look at a problem like, let's suppose we want to determine sine 29 degrees. I have no idea. I know sine 30 is 0.5, but to give you an approximation of sine 29, I would have never even dreamt about. But now I can. As long as I identify the function, what x is, something that I know everything about, what dx is, then the rest will follow. And I will be able to approximate this. And you can say, just grab your calculator, punch it in. True. But this is the wonders of calculus. We want to use calculus for this. So, first I have to identify the function. Which function did I use in creating this example? Of course. Eventually I will need the derivative. How much is f prime of x? Very good. What is x? Very good. What is dx? Sorry. X is something that we know about, and 30 is the closest. You cannot use 45. You can say, but I know everything about 45. I also know everything about 0, sine 0. But I have to be as close as possible. Otherwise, I will mess up and the approximation will not work that well, right? Because if this is 45 degrees, then the approximation will not be an approximation. It will be too rough, too far away. Very good. So x is 30 degrees. How much is dx? Careful. We do not use degrees in calculus. Yes, if I plug it in a function, in a trig function, but not if it's a standalone. So this would be negative pi divided by 180 in radians. I don't have to write radians once I see pi, it's clear, but let me write it this time. We do not use standalone degrees in calculus. Everything has to be changed into radians. But if I plug in 30 degrees in sine, it doesn't matter. If it's pi over 6 or 30 degrees, there is no difference. The answer will be the same. Very good. So then now we are prepared. So this is x and dx. So x is 30 minus 1. It's 29. The function is sine x. What do I have to write next? The function of 30. So sine 30 degrees plus the derivative, very good, cosine 30 times exactly negative pi over 180. Perfect. So now I can write the equal symbol. At this point, this equals. That's correct. This does not equal that, but this equals what's next. Sine 30 is 1/2. Cosine 30 is the square root of 3 over 2, and I should have put minus because there is a minus there. I should have not rushed to put plus. Sorry about that. Very good. So now minus pi, the square root of 3 over 2 times 180, which is 360. You do not have to do anything else. That's all we care about. Now you can say, wait a minute, show me.